All right, so let's pick up where we left off. We're going to start with number 4 on the angular homework. This is more of a kinematics type problem. We are given an angular acceleration, so that's alpha. So I'm going to go through the process of labeling all the things. A maximum speed of, so we're starting from rest, so omega naught I is 0. And then we have a maximum speed, and that's, I got to look at that units. That's revolutions per minute. So that's not a V, that's really an F, and that, because it's revolutions. So I'm going to say the F is, I'm going to translate that divide by 60 to say that is 200 revolutions per second. Okay, so if I want what is a maximum speed in radians per second, well, then I just want some omega final. And omega final is simply going to be 2 pi times the frequency, because I know what the final frequency is. And so when I multiply them together, I get 400 pi, and 400 pi is 1260 roughly radians per second. Okay, so I don't use the acceleration there because I don't have the time that it accelerated nor the angular distance. Now I can look at the time, and to reach that, go from rest from that. So kinematically, we know that alpha is equal to the change in omega over time. So it follows that time it takes to do that is going to be equal to the change in omega over alpha. Okay, so we have those numbers. You can plug them in, and you get about 84 seconds. All right, which is quite a bit of time. So I don't know how realistic that circular saw problem is. That's definitely not, it should be probably closer to 8,400 for an acceleration, because the circular saw can get up to maximum speed very, very quickly. All right, now how many revolutions does the saw make while accelerating to its maximum speed? Okay, so in other words, revolutions goes along with theta, but theta is first done in radians. So we're going to find theta in radians first and then convert that to revolutions. What do we have? And so we've got alpha, we've got omegas, and we got times. So there's a host of equations we can use. I'm going to go theta equals 1/2 alpha t squared. Okay, you could also do average omega times t would work. So if I put in the numbers, I'm going to get 5250 radians. Okay, and then translate that by dividing by 2 pi, I get 8400 revolutions. So if you got the 5250, that's fine. I mean, the radians to revolutions, I want us to be able to do, but it's not a big deal. And then we want to slow it down. We slow it down in a very short period of time. What is going to be the angular acceleration? So once again, we can just use delta omega over t because we have that information. And if we plug in the numbers, we get 3100, right? So we're going to, our initial omega is going to be the 1260 radians per second. We're going from that to 0 in a very short period of time. Moving on. Again, looks like another type of kinematics problem. Okay, so I'm just going to set up the equations. And let's look at what we have. We have initial speed, so that's a v naught. Okay, distance, so that's just going to be some x. Each wheel and tire is an overall diameter, so I'm going to quickly convert that to, once again, we see that same radius. I don't know why that's so popular. Okay, so radius is 0.35 meters, determine the following. All right, initial angular velocity. So we're not going to use any angular kinematics because we don't have any angular information. All we've got is linear, and the connection between angular and linear velocity is simply that. You can put in the answers, and that should come out to be radians per second directly. Total number of revolution makes before coming to a stop. So again, it's revolutions. So that screams theta, right? But our answer first is going to be in radians. And again, we don't have any angular stuff except for the omega. If we had a time, we could do that. But we can connect this to distance, x, right? So in the other problems, it's s, but it turns out to be the same thing. So theta, by definition, is a linear distance, x over r here. So that's going to be the 115 divided by 0.35, and you will get 329 radians. And then you got to convert that to revolutions by dividing by 2 pi, and that's where the 52.3 revolutions come in. All right, angular acceleration. Well, now I have enough kinematic information that I can set this up. Okay, so I can say basically angular acceleration. I'm going to not just solve for it. I don't have any time yet, but I do have a theta and I do have an omega. So I can say that omega squared equals omega naught squared plus 2 theta alpha. Okay, and we started from rest to rest, or we're finishing at rest. So anyway, alpha is going to be omega squared, omega naught squared divided by 2 theta. And we want everything in radians here. Okay, so if you do that, you'll get 0.88 radians per second squared. Now we can look for the time. The time now should be pretty trivial. You can use time is equal to your change in angular velocity over alpha. You could relate it to the initial and final one. I'll let you work that one out. All right, initially before braking, what part of the wheel, this tire, is moving 8.4 meters per second? So if we've got a wheel like that on the ground, understand it's the center of mass that's moving that. This part, at the moment that's touching is 0, so if this is 8.4, then this part up here has to be moving twice that, 16.8. That's an important thing to understand about rolling. Continuing on. So we have a human centrifuge, so it sounds like we are going to be talking about accelerations. So we're going to make in 1 minute, so that's a time, so I'm going to quickly, t is 60 seconds. I think I'm going to want to do that. 20 revolutions, that's a theta, and that's going to be equal to 40 pi radians. I can get the exact number later. Be reaching its final speed. What is the angular acceleration? Radius is given as 4.1 meters. Okay, so I've got a time, I've got a theta, I want angular acceleration, and our initial speed is 0. So that screams equation theta equals omega I t plus 1/2 alpha t squared. This is 0. And so I can find it as alpha is twice theta all over t squared. Okay, so I've already converted time to seconds. I got this in radians, so make sure you put that value in radians and multiply out by pi, and you get 0.07 radians per second squared. Okay, now final angular speed in radians per second. So, well, what do we have? Well, we've got acceleration, so I can say final omega equals initial omega plus alpha t. Alpha is 0.07. We've got 60, so that looks like that gives us 4.2 radians per second. Final linear speed, well, we got omega, so final linear speed is omega r. So I'll let you put those numbers in, and you should get 17.2. And then how many g's of acceleration is experienced at this one? So what type of acceleration are we talking about at this final speed? That's the radial acceleration, v squared over r, right? That's the whole point of doing a training. So 17.2 squared divided by 4.1, and then ultimately I'm going to divide it by 9.8 to get it to the number of g's, and I get about 7.4. So that's at the threshold where we're ready to pass out. Not very comfortable, we got to get used to it. Okay, let's continue on. All right, so we have some ranking problems, and we want to rank the radius of the sphere. And what are we given? We're given a linear speed and a angular speed. So basically, if we know that v is omega r, r is going to be v over omega. So the ones with the greatest ratio of v over omega are going to give us that. You can work out the actual calculations, but this is, right, all these are the same. A and E are the least. Okay, moving on. Rank their angular displacements after rolling for 2 seconds. Okay, so how are you supposed to do that? Well, angular displacement is theta, and a theta is, since it's constant, it's just going to be omega t. So in this case, it's the one with the greatest omega that is going to give us the greatest angular displacement. So that's E, F, D, A equals B equals C. Okay, so if you have any questions, make sure you let me know. Hopefully this is making more sense. I do apologize about all the revolutions to radians and vice versa. That is the most annoying part from my mind, but we want to be aware of that because very often when you measure things, it's revolutions per minute per second, but in the physics we have to have it in radians because that's the standard unit.